Hello everyone, welcome back, and I'll continue discuss about linear regression. A little disclaimer: I'm not a professional on this topic. I'm also a student, and if you are looking for a professional explanation, it's not the case. I just trying to deeper my knowledge by recording these videos and explaining the way I understood it. So we stopped in the moment where we understood about how we can build our linear model on the two-dimensional space. And basically linear model is a plain line, is a line, just a line, sorry, and in two-dimensional space. So before we move forward, let's build our model in three-dimensional space. So here, if we have three-dimensional space, if we have more than one feature, and yeah, I mean, if we have exactly two features for three-dimensional space. On the slide, we see a multivariate linear regression model. Instead of fitting straight line, we now fit a plane in three-dimensional space. We have axes d1, d2, and y as a target. And orange dots are objects, data points, and we have general form of our function, and we will try to build a linear model that can describe our data in the best possible way in three-dimensional space. So as we can see, we have two features, and hyperplane was built. And this looks like the best linear model that can describe this particular data set, because as we can see, all of our data is mostly exactly on this plane. So basically, all those that we can apply in two-dimensional space, they are all the same for three-dimensional space. We can play with our bias, we can play with our two of our coefficients to affect our slope in one or another way. So all these things, we can manipulate them to find the best possible fit of our model into our data. So that was additional explanation of how we can build our model in three-dimensional space. If we continue, we derived equations that show what forecast the model will give for each object if we specific values of beta are substituted, and we got particular plane. So if we substitute later our some of our objects, and we'll get particular prediction for these particular objects, depending on what kind of plane we had. But important question, an important problem of linear regression is which b coefficients to choose. And here again, quality functional comes into the play in our game. Again, MSE, we want to find the model parameters for which the mean squared deviation is minimal. Again, we can quickly remind ourselves the formula of MSE. For example, if we had just three objects, so basically the whole of our prediction is here, in this function within our linear regression is here, and this is our modified MSE function formula in case of we having three objects and three coefficients as inputs. And what we will do, again, we will just substitute every object into our formula and summarize the whole result and divide it by 3 to get MSE. So basically, the whole formula, if we opened up our summarization process, it will look like this. It will look like we have first object with its data as inputs, these features, and we have our second object here, and we have third object right here. In this case, we can see that we don't have our second feature in this case. So formally, we pose the optimum parameter search problem, and imagine our model is a plane in a feature space. We have our parameters beta that determine slope of this plane, and b0 determines its height, vertical shift. Why do we need intercept in this case? Without it, the plane is forced to pass through the origin, through the 0, 0, 0, 0 at the beginning of our axis, but it's strong restriction for us. So I already discussed it before, that we have to add particular value to tune our model to find the best possible fit. So what needs to be done? We reduce the problem of training the model to the train. Right now, we have to find the way how we can minimize our loss function, our MSE, how we can find such our coefficients beta 1, 2, or 0, that we will get smallest possible MSE. So for this, we need to understand how our functions minimized in mathematics. So later we'll discuss derivatives and learn how to find the points of minimum and therefore the optimal weights of our model. Because if we have multidimensional space, we cannot just visually move, uh, we cannot just move our graph, our plane this way or another. We have to find a more precise and accurate way without visual representation. Again, quickly we can look at another example, visual representation in a three-dimensional space. We have our data in three-dimensional space with two features, one target axis, and we try to find optimal parameters of our beta. In this case, we don't start from the 0 in the beginning of our axis. We have our bias, our beta 0, 5. So because of that, our model is higher than the ground. Our plane is higher than the ground. And in that particular point, we are adjusting slope beta 1 and 2 to find the best possible fit. And we can see that these points These points have yellow lines. Uh, these are deviations. These are deviations, these lines are deviations of how far our model is from our data set. So each object has particular deviation, a line, and that is describing the same error loss function for a particular object. By subtracting value of our predicted value of our plane that we think this value should be, we subtracted from our real target value, we got this particular line, our mistake that we had. So basically, when we find MSC, we summarize all of these lines, yellow lines together. We summarize all of them, and basically we just divide divide that sum by amount of numbers we have, amount of objects we have, and we got mean error. Basically, that's a visual way how we can understand our error at the graph. Okay, we can move further. So basically, how we can find it. Um Again, we would look at example with sample data set where we have two features and bias and our target vector y. We're trying to predict stock price using available features by minimizing our beta coefficients. Sorry, by minimizing our quality functional value. Find the best beta coefficients. So how we can do that? Mathematically, we can write it as our quality functional and leads towards minimum over our beta coefficients. And basically, general form of our um, linear regression is again here. So we substitute all those values into for every object we had. For beta 2, we substituted with 0. For our second object, sorry, yes, for third object, and so we finally got substituted version of the same formula, also with open sum, with sum written step by step. We got this kind of formula. In this formula, we have to apply some mathematical rules in such a way that we can minimize our quality functional with respect to our beta coefficients. So we will talk about how we can find this on the next video. Alright, thank you for watching, and let's quickly summarize what we just learned. We learned how to formally start the task of finding optimal regression parameters. Now we need to learn how to find the minimum and maximum of mathematical functions. And we'll talk about this on the next video.